Hi everyone, thanks for tuning in. Today I'm going to be talking about my experiment entitled What's Up with Emission, in which we investigated blackbody radiation, the speed of light, and line spectra. So to start, I just wanted to give a brief overview of what I'm going to be discussing today. First, I'll cover an introduction, and then I'll go into the theory and methods, and then I'll cover the results and conclude with a discussion of the limitations and improvements for those results. So the overall goal of this experiment was to study some important concepts surrounding light and energy, as they provided some important evidence to the existence of quantized electronic structure in atoms and molecules. And this experiment was broken down into 3 separate parts. So the speed of light will be measured, and the line emission spectra of hydrogen and deuterium will be investigated, and the temperature of potential blackbody emitters will be calculated. As we all know, the speed of light is an important constant that can be applied to many equations to model different physical and chemical processes, and this value can be measured by timing how long it takes for light to travel a known distance. As for line emission spectra, they are based on the fact that atoms have different quantized electronic energy levels shown in the figure here, and we can predict these levels using the Rydberg equation, which relates the principal quantum number and the Rydberg constant to the wavelength. And the Rydberg constant measures the strength of interaction between an electron and a proton. And these kinds of spectra are important because they're characteristic to each element, so they can help in identifying elements in a sample, for example, via the analytical technique ICP-AES. On the other hand, blackbody emitters are important because they allow us to determine things like temperature or intensity solely based on wavelength of emission, or vice versa. And these types of emitters release radiation over a range of frequencies when heated. And the temperature of these emitters can be determined via Wien's equation, which basically just shows that hotter blackbodies emit shorter wavelengths of light. In this figure here, we have showing a blue star that emits a lower wavelength and is hotter than a red star that emits a longer wavelength. And blackbody emission can be theoretically predicted via Planck's equation. And this allows the wavelength of light to be used to predict the intensity at which a blackbody will emit. And this can be used to determine how closely an emitter behaves as a blackbody. And this was a really revolutionary equation as it solved the UV catastrophe of the previous model for blackbody emission. So this equation basically just said that the wavelength of maximum emission should decrease all the way down to 0 as the object got hotter, which is clearly not possible. So Planck's equation is a big improvement from that. And lastly, I just want to cover my hypotheses. So in my first hypothesis, I predicted that the incandescent bulb will better correlate to the blackbody emission profile compared to the LED and the fluorescent bulb. This is just based on how these different types of bulbs produce light. In the incandescent bulb, you have light being produced from heat, but in the LED bulb, you have a combination of different colored phosphors being combined to make white light. And then in the fluorescent bulb, you have a combination of the emission lines of mercury interacting with a fluorescent material to produce white light. So that's why the incandescent bulb should be better correlated. And then for my second hypothesis, I predicted that the intensity of emission lines will be lower for smaller wavelengths. And this is because high energy transitions are less likely to occur because there will be a smaller population of electrons in excited states of high energy. So smaller energy transitions will be more frequent. So the first aspect of this experiment involved measuring the speed of light using an oscilloscope. And this was the setup we used here. A laser is first incident on a beam slitter, which sends light to one detector and to a mirror some distance away. And the mirror is going to reflect the light onto a second detector, both detectors are going to be connected to the oscilloscope, which just tracks the time at which the laser is incident on each detector. And using the path length that the light travels, as well as the time, we were able to calculate the speed of light. And the measurement was just repeated for 5 different distances. Next, the line emission spectra were obtained for hydrogen and deuterium using gas discharge lamps. As shown in the figure, the light sources, which are the gas discharge lamps, are first incident on the optical cube, which was just used so that both of the light beams would be incident on the entrance slit, which then leads to the dispersion device, which then would lead to the exit slit, which would allow the light to be incident on the photomultiplier tube, which then converts the incoming light to an electrical signal. Finally, the Blackbody emission spectra were taken, and a standard ocean optic spectrometer was used with a fiber optics cable to do so, and 7 different light sources were measured in this experiment, and 6 are shown here, and the optics cable was just moved between each light source until the desired spectrum was obtained. Now diving into the results of this experiment, the speed of light measured showed little variation between the actual value, with a percent difference just under 10%. And we found that the measurements became more accurate as the path length was increased. So this comes from the small distance in our setup where the light had to travel from the beam splitter to the first detector. So that resulted in the distance traveled being slightly unequal between the outgoing and returning beams. So this is one improvement we can make to our experiment. We would increase the path length of the light being traveled, and some other improvements, we could also just use a larger sample size overall, or something like more accurate measuring tools. Second aspect of this experiment centered around blackbody radiation. So after we got our emission spectra shown in the bottom figure, the temperature was determined via 2 different methods. Wien's method uses the wavelength of maximum emission to determine the temperature of a blackbody. And I have this wavelength shown here for the fluorescent bulb in blue and for the incandescent bulb in the green. And the sun was calculated to have the highest Wien's temperature at around 6,000 Kelvin. So the temperature of each blackbody was also determined via Planck's equation. And this was done by changing the temperature value until the experimental spectrum fit best to Planck's equation. And it was found that the sun and the incandescent bulb showed the best fit to Planck's equation. But on the other hand, the LED and the fluorescent bulb showed the worst correlation to the blackbody emission profile, which was actually what we predicted in our first hypothesis. Overall, the Planck and Wien temperature matched pretty closely with standard deviation values around 10, and both models showed the same trend in temperature, with the sun having the hottest temperature. However, they both predicted values around 6,000 Kelvin for the temperature, which is pretty different from the actual core temperature of the sun, which is around 15 million Kelvin. And this is just because these emission measurements better reflect the surface temperature of the sun, which is around 6,000 Kelvin. Lastly, getting into the line spectra portion of this experiment, 5 emission lines were found for both hydrogen and deuterium, and lambda max was determined for each, which allowed us to determine the corresponding energy levels, as shown in this table below. And it was found that the lines at shorter wavelengths had smaller intensity, which is consistent with our second hypothesis, because there are less atoms in those high energy excited states to allow for those high energy transitions to occur. And another aspect to note in our spectrum is that the lines are not as narrow or sharp as they would be theoretically. And this has a lot to do with broadening, which can come from pressure broadening mainly, or Doppler broadening, or the uncertainty effect. So this is just one limitation of this kind of experiment. So next, the Rydberg constant was determined both experimentally and theoretically. And the wavelength of maximum emission values and energy level transitions shown on the previous slide were used to create a plot of this plot shown here for hydrogen. And in doing so, we were able to obtain the slope, which is equivalent to the Rydberg constant. And the same procedure was followed for deuterium to determine these values shown in the table. And then R was also calculated theoretically using Bohr's equation, which is dependent on the reduced mass of the atom. And the percent difference was relatively small and similar between hydrogen and deuterium. But one limitation of the Rydberg equation is that it does only work for hydrogen isotopes. because they are all one electron systems. So if we wanted to repeat this for a different element, we would not be able to. So the Rydberg constants were then used to calculate the ionization energy and nuclear mass of deuterium. And a form of the Rydberg equation, a simplified form, was used to calculate ionization energy after plugging in these values for N. And the theoretical calculations were performed in the same way, using the literature values of the Rydberg constant for hydrogen and deuterium. And there was actually very little difference between the experimental and theoretical values, but there was a slight difference between the hydrogen and deuterium ionization energy. So the ionization energy of deuterium was slightly larger than that of hydrogen due to the larger mass coming from the extra neutron in the deuterium isotope. And the nuclear mass of deuterium was also determined experimentally using the relationship of the Rydberg constant to the reduced mass of the system. And then the theoretical mass was just assumed to be 2 times that of the hydrogen atom. And the calculated value, experimental value, was slightly smaller than the theoretical value by about 11%. To sum up the presentation, I wanted to go over some conclusions that can be drawn from these experiments. In terms of the speed of light, as discussed before, the path length does affect the accuracy of the measurements. And in the blackbody radiation portion of the experiment, it was found that the sun and the incandescent bulbs did follow Planck's model the best. And both Planck and Wien models were consistent in that the sun was the hottest emitter for each model. Lastly, the line spectra showed that the intensity decreased at short wavelengths, and it was also found that deuterium has a larger Rydberg constant and ionization energy than hydrogen. And while these experiments seem to study different aspects of light and energy, they were all important in providing evidence for existence of quantized electronic structure in atoms and molecules, which really revolutionized the way that we think about chemistry. Finally, I just wanted to include my references and to thank you for watching.